So let's explore a little bit more about this equilibrium constant for water, the auto-dissociation or auto-ionization of water. And so that is Kw. It's 1.0 times 10 to the minus 14th. Probably the most important equilibrium constant value for this class. No doubt about it. And that's just simply the concentration of H plus times the concentration of OH minus. And that comes from the auto-ionization of a water molecule. In a previous video, we also talked about how you could consider two water molecules reacting with one another, one as an acid and the other one as a base, but that just gives you the hydronium ion instead. And so you could, anywhere where we see H+, you could also call it the hydronium ion. Okay, so, and so this allows us to calculate various other things. Also the definition of pH. So pH is just simply the negative logarithm, base 10 logarithm of H+ concentration. It's an easy way to deal with a large range of hydrogen ion concentrations from basically 1 molar all the way to 10 to the negative 14th molar. Okay. You should also know that there's nothing that limits our concentration to between these values. Okay. Why couldn't H plus have a greater molarity than 1 molar, or a smaller molarity than 10 to the negative 14th molar? In fact, it can. And so if you have something like 10 molar, a 10 molar solution, what would the pH of something like that be? Right? What kind of pH? Okay, well, that's pretty easy to figure out. pH is the negative base 10 logarithm of 10. Okay, and so the logarithm of 10, what power do you raise 10 to get 10? The first power. And so this is negative 1. So the pH is negative 1 at that point. Okay, and so you can in fact go below a pH of 0. We just normally talk about it starting and stopping at 0 and 14, but that's not true. 0 does not really mean 0 here. It means 1 molar H+. So if you have 10 molar H+, a factor that's 10 times as concentrated in H+, it'll just keep going on. This is a logarithmic scale, and all of these numbers here are powers of 10. Okay, and of course, if you had something like a very, very small concentration, right, 10 to the negative 16th molar H+, right? Well, that would actually imply that your OH minus concentration is really high, okay? About 100 molar. I don't know if that's possible for some type of strong base, but that's what it would be in theory. And in that case, in a situation like that, like 100 molar in a OH, I don't think that's physically possible. That much NaOH won't dissolve in water. But if it could, then you'd be dealing with something at a pH of 16. That is to put some things in perspective and to clarify the pH scale a little bit for you. Okay, but in general, 0 to 14, but it can go below 0 if it's really, really, really acidic, or even just like 10 molar H+, and can go above 14 if it's really, really basic. Okay, so here's the idea. If we know H+ concentration, we can figure out OH minus concentration. In fact, I just did that a moment ago. How did I figure out this 100 molar right here? It's tied together with this equation. Since we know, imagine if we knew H+, how could we find OH minus concentration? Well, we would take Kw, 1.0 times 10 to the minus 14th, and divide it by the H+ concentration. Okay, and if you had the OH minus concentration and you wanted to find H plus concentration, you could take the Kw value and divide it by OH minus concentration. And that would allow you to move this direction, okay? And of course that's going to equal OH minus concentration that way, and that's going to equal H plus concentration that way. Okay, so you can go back and forth between these. It's held together from this equilibrium constant. Whenever you have water present, this equilibrium, this autoionization of water is always going on. It's about 1 in 10 million water molecules that do this. Okay, it's not a lot of water molecules dissociating, by the way. Water is a very, very poor electrolyte. On the flash drive lesson yesterday, they talked about that water is a very poor electrolyte. Okay, and so that small value helps us understand, like, okay, well, what's favored here? Is it the reactants or products? Small k means reactants are favored. There's a lot more undissociated water molecules in water than these ions. I forgot to put the aqueous thing there. Okay, now if you want to know H plus and you know pH, or vice versa, if you know H plus and you want to find pH, well, we talked about how to do that just a moment ago, actually. Okay, so pH is defined to be the negative log of H plus concentration, and you could go back the other direction. To undo a logarithm, well, first we got to divide both sides or multiply both sides by -1, so negative pH would be the logarithm of H plus, and then to undo the logarithm, that would be 10 to the 10 raised to the power of each side. So H plus concentration, how could you find that if you knew the pH? That's going to be 10 raised to the negative pH. Okay, that's how you undo the logarithm, right? And there is such a thing as pOH. If pH is the negative base 10 logarithm of H plus concentration, well, pOH is the negative base 10 concentration of OH minus concentration. So a lot of people know about pH, a lot less people know about pOH, but it's an equally valid thing to talk about in a solution, but people tend to talk about pH. Okay, so if you know OH minus concentration, pOH would just be the negative base 10 logarithm of OH minus concentration. And just like we did over here, you could undo that logarithm, and OH minus concentration is going to be equal, let me move that over, didn't quite put it where I wanted it. OH minus concentration is going to be equal to 10 raised to the negative pOH. Okay, now finally putting it all together, it's kind of substituting in together, it can be clearly shown that since, well, the simple thing to do here is to take this equation, and if you work with this, and maybe I'll leave it up to you to kind of establish this, but let me just give you the result. It turns out that the sum of pH and pOH equals a very simple number. Take a guess. What do you think pH plus pOH might equal? 14. The sum of those is always going to equal 14. And that's good to the hundredths place. Okay, and that basically comes about by taking the negative base 10 logarithm of both of these sides here. So if you know pH, how can you find pOH? Simple. 14 minus pH is going to be pOH. And if you want to know the other one, well, 14 minus pOH equals pH. So these are all connected in various ways, and if you know pH, for instance, there's a couple ways that you could move along this table to figure out OH minus concentration or something like that. But anyway, there's more than one way to skin the cat in this scenario. If you know one thing, you can figure out all of these other things on here. Okay, so with that, let's do a little practice problem. What's the OH minus concentration, pH, and the pOH of a 0.1 molar solution of HCl? Okay, so almost similar to a problem from yesterday on yesterday's assignment. What's the pH? Well, let's start off with this fact right here. It's 1 molar HCl. Now HCl, hopefully you remember, is a strong acid. That means it undergoes 100% dissociation in water. So if you have a 0.1 molar solution of HCl, that is going to be 0.1 molar H plus and 0.1 molar Cl minus. Now, which one of these is relevant for what we're talking about? This one right here, the H plus concentration. Okay, so they've basically told us that, but this is a strong acid, so we get 100% dissociation. That's important to remember. Okay, so how can we find pH? pH is going to be the negative base 10 logarithm of H plus concentration, which is the negative base 10 logarithm of 0.1. And what power do we raise 10 to get 0.1? We raise it to the negative 1 power. And so negative 1 is 1. Okay, so our pH is 1. Let me talk about significant figures for logarithms. So sig figs for logarithms. Logarithms, okay. It is not what you might think here. Although if you're thoughtful, it might make sense here. Imagine we have the xy axis and we're graphing y equals log natural logarithm of x. It could be any type of logarithm, natural logarithm of the weather, whatever. It kind of looks something like that, right? And so notice that as x is increasing, y is increasing a lot more slowly, okay? And so if you know x very, 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 very precisely, you might actually know y even more precisely, okay? Because of this kind of slowing down, all right? In other words, if you jumped up a unit over here, you're going to only be jumping up a fraction of a unit over here on this one, okay? Now the result of this is you can summarize it by saying something like this. The number of sig figs in the argument, and for this case we're talking about either H plus concentration or OH minus concentration. The number of sig figs in these values is equal to the number of decimal places in the logarithm. And I'm probably misspelling logarithm. Sorry, English people out there. English experts. Okay, so, and what's the logarithm for us? The pH or the pOH. And let's just see if that makes sense. I'm gonna grab the calculator and we can try a couple examples here. And maybe I'll write out the examples and see, we'll type in the negative base 10 logarithm of, let's say, 0.100, like we just saw before. And let's change it by just a little bit, 0.101, a little bit bigger. You know, if somebody measured H plus with this value and somebody else measured it with that value, those would be comparable measurements. You know, both valid measurements perhaps. What would happen to the pH here, okay, from this value and this value? How would they differ? So let's grab the calculator and just test it out. Okay, so we're going to type in the negative base 10 logarithm of 0.100. Of course, the calculator doesn't care if I put those extra zeros there, and we see that's 1. Now let's change it just slightly. The negative base 10 logarithm of 0.101. Somebody else might have measured the concentration of H plus that way. And here we can see that the difference between this number and this number lies in the thousandths place, which is the third decimal place. Okay? Up here we typed in 0.100. It had 3 significant figures. This one also has 3 significant figures, and we're off only in that third figure. And here we can see that the number of significant figures equals that decimal place number where we start having the variation. Okay, and so let's try one more example. So 1 versus 0.996. Where should we round the answer if we're seeing our variation this way? This one, it looked like it might be exactly 1. This one gave us 0.995 something or other. 679. Okay, so it's only off in, in this spot here. All right. So we're gonna round our answer regardless to the thousandths place in our pH. Okay, because that's the spot where we have the variation, and that is 3 decimal places when I used values of concentration that had 3 significant figures. Okay, and let's just do one more to illustrate that. One more example. Let's have a negative log of 0.59 versus negative log of 0.58. Okay, so the prediction is we've got 2 significant figures here. So in the pH, it's going to be off in this decimal place here, the hundredths place. 2 decimal places. That's where our uncertainty will be, and we should round it to the hundredths place. So let's just verify that. Okay, negative logarithm, base 10, 0.59, and negative logarithm, base 10 of 0.58. Okay, and there we can see this one gives us 0.229 and 0.236. Okay, and so where are we seeing the variation? This one and this one, right? So it's off in the second decimal place. So I would round this one to 0.23 for the pH, and this one I would round it to 0.24 for the pH. Okay, so that's the rule for significant figures for logarithms. And so why was I doing all that? Because up here I was wanting to know how precise I should be, and we've already seen how precise I should be. This is going to be, we've got 3 significant figures here, so we're going to round this to 3 decimal places. That's the pH. Fairly precise pH, okay? And how could we find POH? POH would be 14 minus pH. So the POH, 14 minus pH, so 14 minus 1.00. And so POH is 13. They should add up to 14. And so what is the concentration of OH minus going to be? We're almost done. We found the pH, found the POH. We just need OH minus concentration. Well, I know this one now, I know this one, and I know this one. I could use either one of these to figure out the OH minus concentration. Okay, so the one that I normally like to do, just because I remember the KW value, is this one here, KW divided by H plus concentration. Okay, so KW so that's going to be pretty simple, 1.0 times 10 to the negative 14th over 0.1. Okay. And so dividing by 10 is the same as multiplying, dividing by 1/10 is the same as multiplying by 10. And so we get 1.0 times 10 to the negative 13th. We could have also arrived there by recognizing OH minus concentration is going to be 10 raised to the negative POH. Okay, so maybe that's even easier, 10 raised to the negative 13. Okay, and the number of decimal places in my pH becomes the number of significant figures in my concentration. Okay, and so that is the concentration of OH minus. So we found all 4 of them now. Ooh, that's this chloride, which I don't really care about. H plus. Okay, so there's all 4 of them. All right.